Welcome back, Physical Science 20. This is the next section in the Properties of Waves booklet. So continuing on with sound waves, we looked at basically what type of waves sound waves are, and also how we can determine the speed of sound in air at various temperatures and the speed of sound in various other materials. And we kind of alluded to how we detect them, but we'll take a look now at detecting of pressure waves. So sound detectors transform sound energy, the kinetic energy of the vibrating particles in the medium, whatever is transmitting it, into another form of energy. A common detector is a microphone, which transforms sound energy into electrical energy. A microphone consists of a thin disc that vibrates in response to the sound waves and makes an electrical signal with that. If we look at the human ear, so we have that and the various pieces here of the inner ear. It's a sound detector as well that receives pressure waves and converts them into electrical impulses as well. The tympanic membrane, also called the eardrum, vibrates when sound waves enter the auditory canal. So this is like our microphone here, a little disc here that vibrates in response to the vibrating air molecules that are entering. Three tiny bones in the middle ear then transfer these vibrations to fluid in the cochlea. Tiny hairs lining the spiral-shaped cochlea detect certain frequencies in the vibrating fluid. These hairs stimulate nerve cells which send impulses to the brain and produce the sensation of sound. So from there we have the three tiny bones, etc., and then that signal gets transferred into an electrical signal which our brain interprets as sound. Quite amazing. The ear detects sound waves over a wide range of frequencies and is sensitive to an enormous range of amplitudes. In addition, human hearing can distinguish many different qualities of sound. Knowledge of both physics and biology is required to understand the complexities of the ear. The interpretations of sound by the brain is even more complex and still is not totally understood. Okay. Perceiving sound. How humans perceive sound depends partly on the physical characteristics of the sound wave, such as frequency and amplitude. So if we look at pitch, pitch is the highness or lowness of sound. It can be given the name on the musical scale. For instance, the note of middle C has a frequency of 262 hertz. The highest note on a piano has a frequency of 4,186 hertz. The human ear is not equally sensitive to all frequencies. Most people cannot hear sounds with frequencies below 20 hertz or above 16,000 hertz. And in class, we'll likely do a little test just to see what frequencies can you hear. Can you hear between 20 and 16,000? Or can you hear a little bit beyond that range? Many animals, such as dogs, cats, elephants, and bats, are capable of hearing sounds at frequencies, of course, that humans cannot hear. So the old dog whistle, dogs can hear it, but humans can't. So pitch really is frequency, which in layman's terms is the highness and lowness of sound. Loudness, frequency, and wavelength are two physical characteristics of sound waves. Another physical characteristic is amplitude. Amplitude is the measure of the variation in air pressure in the wave. The loudness of a sound is the intensity of the sound as it is perceived by the ear and interpreted by the brain. The intensity depends primarily on the amplitude of the pressure wave. So, and we looked at what amplitude actually is. So if we imagine waves as being transverse waves, of course it is that initial pulse. How big is that pulse initially? I'm just trying to look back and see if I can find it here. Right back. Oh, one more yet. One more yet. Right back here, amplitude. So how big the pressure wave is. Big amplitude versus small amplitude. So that's what it looks like on a transverse wave. So that, of course, is what we interpret to be as sound loudness. By the ear and interpreted by the brain, the intensity depends on the amplitude of the pressure wave. The human ear is extremely sensitive to variations in the intensity of sound waves. Recall that 1 atmosphere of pressure is that many pascals. We didn't take that, but for interest, there it is. So we have various different pressures here, and that is, in turn, the loudness. Driving over a mountain pass changes the pressure on your ears by thousands of pascals. Pascal is a unit for pressure, by the way. But this change does not take place at audible frequencies. Because humans can detect a wide range of intensities, it is convenient to measure these intensities on a logarithmic scale called the sound level. So loudness, we kind of measure it in terms of decibels, and you've likely heard of that before. The most common unit is decibel. The sound level depends on the ratio of the intensity of a given sound wave to that of most faintly heard sound. The faintest sound is measured as 0 decibels. A sound that is 10 times more intense is registered as 10 decibels. I'll get you to change that to a 10. A sound that is another 10 times is 20 decibels. So for every increase of 10 on the decibel scale, it increases by a factor of 10. So if we're going from 10 to 50, 10, 10, 10, 10, 10, that's 10 number 10s multiplied together, or sorry, that's 5 number 10s multiplied together, so that gives us 100,000. Most people perceive 10 decibel increases in sound level as much as 10 as loud as the original level. This figure shows the sound level for a variety of sounds. In addition to intensity, pressure variations, and the power of sound waves can be described in the decibel scales. Okay, so we can see various things here. What is the decibel scale related to in real life? So if we take a look here, we can hear barely audible is at 10 decibels. I believe this is 30, which is a whisper. Casual conversation, 50 decibel. Alarm clock, 80. Rock concert, 110. Jet engine, 140 decibels. So that relates things to real life there, so you can see exactly what that scale represents. So we can see here casual conversation is 100,000 times more loud than a whisper. Alarm clock, 60, 70, 80, that's a movement of 30, so that represents 10 times 10 times 10, 1,000 times louder than that. Going from 80 to 110, 90, 100, 110, so we can consider that 3 movements, or 30 movements, sorry, and each of them is a factor of 10 increase, so that's 1,000. All right, the ear can lose its sensitivity, especially to high frequencies, after exposure to loud sounds in the form of noise or music. The longer a person is exposed to loud sounds, the greater the effect. A person can recover from short-term exposure in a period of hours, but the effects of long-term exposure can last for days or weeks. Long exposure in the 100 decibel range or greater can produce permanent hear damage. Hearing loss can also result from loud music being transmitted to stereo headphones, etc., etc. In some cases, the listeners are unaware of just how high the sound levels really are. Cotton earplugs reduce the sound level only by about 10 decibels. Special ear inserts can provide a 25 decibel reduction. Specifically designed earmuffs and inserts, as shown here, you can reduce sounds up to 45 decibels. So simply using plugs that you put in your ear don't really reduce it by that much. But if you have specially designed earmuffs, 45 decibels, that's a fairly drastic drop. All right, we'll see you again, and next time we'll look at the Doppler effect. But before we do that, the questions you should be able to do now is this sheet right here, detecting and perceiving sound. So if we take a look here, pitch, loudness, what is all of that? And then a couple of questions here on just the decibel scale, and of course the last part mentioning using earmuffs to reduce the number of decibels at each ear. All right, we'll see you again.